Now let's revisit the tangent and cotangent functions that we defined in element 48. Suppose I take an angle alpha in the unit circle. I can associate this angle with two quantities called the tangent and the cotangent of this angle. So we take this ray and we extend it until it intersects this axis, the tangent axis at this point, and this axis, the cotangent axis at this point. Then the tangent of the angle alpha is this length here, and the cotangent of the angle alpha is this length here. If lengths are on this side of the axis and on this side of the axis, they're counted as positive, and if they're on this side of the axis or on this side of the axis, they counted as negative. And so this particular angle alpha has a positive length for the tangent and the positive length for the cotangent. This is the unit circle, so its radius is 1. Now let's rescale the whole picture by a factor of r, so that the circle has radius r, and all distances are scaled by a factor of r, but the shape of the picture is still the same. Now you see that the radius of the circle is r, and then this length, instead of being tangent of alpha, is now r times tangent of alpha, since all lengths got r times larger, and this length similarly is r times cotangent of alpha. Note that this length is also the radius of the circle, r, and that this line is parallel to this line. Therefore, this angle equals this angle, so we can mark this as alpha. Also, we know that this angle is 90 degrees and this angle is 90 degrees, because this line and this line are tangent lines to the circle at this point and this point respectively, and this is the center of the circle. I deleted the useless parts of the picture, and now we see some interesting facts about the tangent and the cotangent. See, in a triangle in which this angle is alpha, this angle is 90 degrees, and this side is r, so this side is known, we can find this side using the tangent function. This is r times tangent alpha. The tangent can be defined in the right-angled triangle with angle alpha as the ratio between this side and this side. Similarly, look at the situation here for the cotangent. We have a right-angled triangle with angle alpha, and this side is r. Then this side is r times cotangent of alpha. So the cotangent can be defined, at least for an acute angle alpha, as the ratio between this side and this side over the right-angled triangle with angle alpha. Let's do this one more time. Suppose we have a right-angled triangle with angle alpha here, and suppose that this side is x. Then we can immediately write this side as x times the tangent of alpha. Similarly, if we see a right-angled triangle where the side against the angle alpha is x, then the other side of the triangle, that's not the hypotenuse, is x times the cotangent of alpha. Now from here, can we find a connection between the tangent and the cotangent? Oh yes, because see, in this triangle, we know that this is 90 degrees and this angle is alpha, and we know that this side is x times the cotangent of alpha. And therefore, we can express this side as this side times tangent of alpha. And so this side becomes x times cotangent of alpha, which is this side, times the tangent of alpha because of this angle, and therefore we have the following equality. Now we can cancel out the x, and we get this equality. Cotangent of alpha times tangent of alpha equals 1, and that's true for all angles alpha. Here are two more ways in which we can write this equality. Now can we find some relationships between the tangent and cotangent and the sine and cosine of the angle alpha? Well, we can. Consider this triangle, in which this angle is alpha and this side is x. It follows that this side is x divided by cosine of alpha, and this side is x times sine of alpha divided by cosine of alpha. And so we got this equality here. We can cancel out the x, and then we get that tangent of alpha equals sine of alpha divided by cosine of alpha. This is not really surprising, because what is the sine of alpha? Let's look at this triangle. Well, it's the ratio between this side and this side. What's the cosine? The ratio between this side and this side. So when we take sine alpha divided by cosine of alpha, this side would cancel out, and we would get the ratio of this side and this side, which is exactly what tangent of alpha is. Now, using this equality for the tangent and the cotangent, we can find that the cotangent of alpha is the opposite ratio, cosine of alpha divided by sine of alpha. By the way, this equality is again not really surprising, considering that the cotangent of this angle alpha, for example in this triangle, is the ratio between this side and this side, and the tangent is the reverse ratio, the ratio between this side and this side. And so this equality must hold. Now take a look at this angle, which is 90 minus alpha, and this angle, which is 90 minus alpha. We know that the tangent of this angle is this side divided by this side, but this is exactly the cotangent of alpha. Similarly, the cotangent of 90 minus alpha here is this side divided by this side, which is exactly the tangent of this angle here, this side divided by this side. Therefore, tangent of 90 degrees minus alpha equals cotangent of alpha, and cotangent of 90 degrees minus alpha equals tangent of alpha. Here's the optional problem. We have a right-angled triangle with right angle here, and this is the altitude in the triangle. This point here is the midpoint of the altitude, and this point is the midpoint of this segment. So this length equals this length. And this is how we construct this red line and this red line. We need to prove that the two red lines are perpendicular to one another. And here's the solution. Let's call this length x, then this length is also x. And if this length is y, then this length is also y. Let's call this angle alpha, this angle beta, and this angle gamma. We know that from this triangle, this angle is alpha and this is 90, and so this angle must be 90 minus alpha, meaning that this angle here is alpha. Then from this right angle triangle, with this angle is alpha, and this side is 2y, we know that this side must be 2y times tangent of alpha. And now we can find the tangent of gamma from this right angle triangle and the tangent of beta from this right angle triangle. So the tangent is this side divided by this side, so y divided by 2y tangent of alpha. Now we can cancel out the y's and we get 1 divided by 2 times tangent of alpha. Tangent of beta is this side divided by this side, so 2y divided by x. Now we can find cotangent of beta by just reversing this ratio. So cotangent of beta must be x divided by 2y. But we know that tangent of 90 minus beta equals cotangent of beta, and hence tangent of 90 minus beta equals x divided by 2y. We need to prove that this angle is 90 degrees, but we know that this angle is 180 minus beta minus gamma, and therefore we must prove that beta plus gamma is 90 degrees, or in other words, that gamma is 90 minus beta. And therefore, if we prove that tangent gamma equals tangent of 90 minus beta, it would follow that gamma equals 90 minus beta, so we would have 90 minus beta here, which would mean that this angle is 90 degrees. So we just need to prove that this expression equals this expression. So essentially, this is what we need to prove. And now we can cancel out the 2's, and now we can reverse the two fractions on both sides, and now we ask ourselves, is it true that tangent of alpha is y divided by x? Well, see this triangle. Tangent of alpha is this side divided by this side, which is 2y divided by 2x, and hence this equality is true. Now we cancel out the 2's and we get y divided by x equals tangent of alpha, which is exactly what we needed to prove.